Hey everyone, and welcome to Adwoa Biotech, where we make biological sciences clear and fun. Have you ever been in the lab running a protein quantification assay, and there are a group of you and everyone gets slightly different results? One person measures 18 micrograms per milliliter, another gets 22, someone else gets 25. So what do? We usually take all those numbers, add them up, and divide by how many measurements we have. That gives us one single number, which is called the average or the mean. It's like saying, on the whole, our samples contain about 22 microgram per mil of protein. That number gives us a quick sense of one typical value in the group. But of course, it doesn't tell us everything. So often, we try to boil down a whole bunch of data into just one single number, the average or mean. But what if I told you that single number is often hiding the most interesting part of the story? Today, we're going to look beyond the average and unlock what our data is really trying to tell us. All right. Let's just jump right in with a question. A student gets a 50 on a test. So what do you think? Is that a good score? Is that a bad score? The truth is, it's impossible to say anything, right? With just me telling you they got a 50. With just that one piece of information, we are missing the most important thing of all, context. And here is the context we are missing. Take a look. In both of these classes, the average score is exactly the same. It's 50. But getting a 50 in class A, where everybody's scores are all clustered together, that means something completely different than getting a 50 in class B, where the scores are, well, all over the place. And that right there is the crucial point. The average tells you about the center, but it tells you absolutely nothing about the spread or the shape of the data. To really understand the full story, we have to look at how that data is dispersed. So let's get the right tools for the job. The first set of tools in our kit are called measures of variability. Think of these as the very first clues in our investigation. They help us understand just how spread out or, clustered together our data points really are. Yeah, measures of variability, they pretty much do exactly what it says on the tin, on the label. While things like the mean tells us about the center of our data, variability tells us about the spread. And I like this example of the height of babies versus the height of adults. In general, the heights of babies are pretty consistent, but there can be huge variability in the heights of adults. So, the measures of variability tells you how far all those different data points stray from that center, which is often the average or also referred to as a mean. A really fantastic and super quick way to get a snapshot of this spread is the 5-number summary. It's awesome. It basically breaks the data into quarters, giving us 5 key landmarks. You've got the absolute minimum or the smallest value. Then you have the first quartile, which is the 25th percentile, it's referred to as the 25th percentile. Then you have the median, this is right in the middle. Then you have the third quartile, which is referred to as the 75th percentile. And of course, the absolute maximum. It's such a powerful summary in just 5 little numbers. And from that 5-number summary, we can instantly calculate 2 really simple measures of spread. The first is the range. The range is the most basic one. You just take the maximum value and subtract the minimum. That gives you the range. But a much more telling measure is the interquartile range, abbreviated as IQR, which tells you the range of just the middle half of your data from quarter 1 to quarter 3. So, why do we often prefer the interquartile range or IQR? Well, it all comes down to outliers. One single extreme score can make the range massive and, frankly, misleading. Just like the quote says, the IQR gives us a much more stable and robust picture because it's only looking at the middle 50% of the data. Now, the IQR is great, but it's still throwing away some of the data, the top 25% and the bottom 25%. What if we want a measure of spread that uses every single data point? Well, for that, we need to bring out the big guns. This is the most powerful tool in descriptive statistics. Meet the standard deviation. Now, don't let the name scare you. At its heart, the concept is actually beautifully simple. It's just a single number that tells you the average distance of each data point from the mean or average. That's it. A small standard deviation means all the data is tightly packed together. A big one means it's spread far and wide. Okay, I know what you might be thinking. The formula for this thing can look a little intimidating, but I promise you the process itself is actually very logical. Let's just demystify it right now by walking through a calculation step by step with the sample set of 6 scores. First things first, we need a center point to measure everything from. So, step 1 is to calculate the mean or average of our data. We just add up all the scores, divide by how many there are, in this case 6, and that gives us a mean of 50. Easy enough. Okay, next, we figure out how far each individual score deviates or strays from our mean of 50. So, for example, the first score is 46. How far is 46 from 50? It means that we have minus 4 points away from the center point. We do this for all the scores to get how far they're deviating from the center, the average, the mean. And then to get rid of all those pesky negative signs, we just square each of those deviations. Now, for the easy part, we've got all of our squared deviations calculated, so we just add them all up. This gives us a total value that we call the sum of squares, which in this case comes out to 886. All right. Now we find the average of those squared deviations to get something called the variance. Now here's a key little statistical detail. Since this is a sample of data, not the whole population, we divide by the number of scores minus 1. It's a technical step that just gives us a better, more accurate estimate. So our variance is 177.2. We are almost there, I promise. So remember how we squared the deviations earlier? That means our variance is in squared units, which isn't very intuitive. So for our first step, we just take the square root of the variance. This gets us back to our original units and gives us the standard deviation 13.31. So on average, each point is about 13.3 points away from the mean. So what does this mean? What does this 13.3 actually mean in the real world? Well, for data that's normally distributed, you know that classic bell shape, curve shape, we can use a super handy rule of thumb called the empirical rule. It tells us that about 68% of all our data will fall within one standard deviation of the mean. 1. So it tells us that about 68% of our data will fall within one standard deviation of the mean. And in our example, that would mean between roughly 37 and 63. So this is a great shortcut for quickly understanding our data. Okay, so we've covered the center of the data and we've covered the spread, but there is one last layer to our story: the actual shape of the data's distribution. These are the finishing touches that complete our statistical picture. Two key measures describe this shape: there's skewness and kurtosis. Now, they sound complicated, but they're not. Skewness just tells us if the data is lopsided, if it has a long tail on one side. And kurtosis tells us about the tails themselves. Are they fat or thin? Which tells us how likely extreme outlier values are. Let's look a little closer at skewness. A distribution that has a long tail dragging out to the right, like you often see with income data, has a positive skew. If the long tail is on the left, it has a negative skew. And if it's perfectly symmetric, like a bell curve, its skewness is just 0. So apparently kurtosis more applies where you're trying to understand risk. So the fatness or thinness of the tail applies when you're looking at risks and the likelihood of it happening. Apparently it's quite used in finance. And a fat tail means that those crazy extreme outlier events are way more likely to happen than you might otherwise expect. But if it's thin, then it's not as likely. Okay, we have assembled our full toolkit. We understand center, we understand spread, and we understand shape. So now let's go all the way back to our original mystery and see just how easily we can solve it. And here we are again. Both classes have an average of 50. Both are symmetric with a skewness of 0. But look at the standard deviation. Class A has a tiny standard deviation of 2. That tells us performance is incredibly consistent. It's predictable. Class B has a massive standard deviation of 40, revealing that performance is wild and totally unpredictable. The mystery is solved. And it wasn't the average that did it. I mean, obviously, if we told you the score is 50, you'd want to know 50 out of what. But that aside, if we're trying to really compare the averages between one and the other, then the average is not what's useful between one group and the other. It was the measure of variability. So the next time you see an average reported somewhere, I want you to be just a little bit suspicious. Don't just take it at face value. Remember that the most important, most interesting part of the story might be hidden away in the spread and its shape.